Hi, hello. Steve George here with Kennametal. Welcome, everybody. Look forward to talking to you today. Really excited to talk with everybody a little bit today about vibration. Um, so this is a topic that there's a lot of us that research it, look into it, and get kind of passionate about it. And yeah, so we'll have a little bit of fun with it today. And we're especially going to talk about how this can affect tools that have long overhangs, especially boring bars, and some solutions that we have for you to be able to use. So before we get started here, let me just let everybody know how you can ask some questions. If you're in the Click meeting down the lower right-hand corner, we've just turned the chat on. Feel free to ask questions, type them in there, and we'll look and answer them as best as we can as we go along. If you're on Facebook, please feel free to leave questions in the comments. We'll answer as many of those as we can as we go along, and the rest we'll try to catch up back with you afterwards. So yeah, so thank you very much. And again, we hope everybody's being safe during this time. We really appreciate that you took time out of your day to watch this webinar and spend some time with us. Just want to remind everybody that, again, this is going to Facebook. This is also going to go on YouTube afterwards, so please feel free to share it with your friends. You can subscribe to our YouTube channel. You can also follow us on Facebook and stay notified. So with that, let's get started. Let's talk a little bit about, what vibration is, and let's talk a little bit about what chatter is. And then we're going to go from there into kind of how this relates to our topic, and then get into some tools. So let's just start with what vibration is, right? So vibration is basically, one of the ways that we can break it down is it's an oscillation. It's an oscillation pattern. And, we're constantly surrounded by vibration all the time, right? If you think about it, the sound of my voice being projected right now is a vibration, right? So my voice box is helping to generate a sound wave, move the air. That's being picked up by the microphone, and again, your speakers are causing a vibration that your ears can then pick up. So that's a very simple example of vibration. We experience vibration in our cars driving every day, or whatever mode of transportation you use. So vibration, it's really all around us, and again, it is an oscillation. So how does that then kind of play into the topic today? Well, basically, when we get into machining, tackling vibration is a really big thing, and for two reasons. So one, just in general, right? We're trying to make the best possible parts we can as machinists, and vibration really plays into that, right? So that could affect surface finish, for instance. There's a lot of different things like that come into play. So what would kind of be the difference between vibration and chatter, for instance? We can kind of think about it like this. So chatter would be an example of unwanted vibration. In general, our tools, our machines, they are always vibrating. They are always moving in space. However, it might be just a slight motion. But where chatter comes in is when we, let's say, exceed the level of vibration that we want to have in the system. Oftentimes, and we're going to get into this a little bit more in detail about what this means, but oftentimes we get into a point of kind of a self-excited vibration that then starts to sort of spiral out of control in a way. We'll talk about that a little bit. And so that's, again, what happens in chatter. In chatter, we can see it, okay? So we see it as a finishing a part. We can hear it, usually, okay? We can feel it in the machine, and it's something that we want to avoid. So I'm going to bring up a few slides now that we'll kind of talk through. In terms of machining dynamics, so unstable vibration is really a major factor of limiting production, especially at high cutting speeds. So a lot of us know that, right? So we talked about how that's going to degrade accuracy and finish. The other big thing to keep in mind, especially in rotating tools, is that it really can lead to premature tool wear and also wear in your spindle bearings. So let's kind of break down a couple different types of vibrations that are present. So the first thing that we want to talk about is a free vibration. So what free vibration is versus forced vibration versus self-excited vibration. So free vibration, the easiest way to think about it, if I take, I'm going to use this little ruler here, but same, good example also is a string, a guitar string, violin string, piano string. You pluck the string, you strike the string, you draw a bow across the string and release it. Okay, it's going to deflect, it's going to move back, and now it enters this pattern of oscillation or vibration until it ends, right? And we're going to talk about what causes that to end and how quickly it ends. So that's free vibration, okay? I've plucked it, I've struck it, but I am not driving it at a frequency. I apply a force, I apply a load, I let it go, and now it is oscillating on its own as a result of the initial force or deflection. Forced vibration, on the other hand, takes it a little bit further. So forced vibration is where we're also applying a load or an external force at a frequency. So a repeated motion, for instance, in a pattern, that would be forced vibration that a system would then have to follow. And then the last part, which a lot of people think about, right, is self-excited vibration. So self-excited vibration occurs when the system is, let's say, starts to take off on its own, right? So a lot of people have seen the famous video of the bridge. So due to high winds, the bridge is moving, okay, and all of a sudden it's in force, but it hits a point that it picks up its first main frequency, natural frequency, and it starts to resonate, okay? And that self-excited vibration is a pattern which rapidly increases. So let's kind of step through here real quick, and we'll talk about again how this kind of plays into machining. So free or natural vibration, right? So again, this is where we had an impulse, okay, we removed it, and the system is now vibrating as a result of that, but will decrease with time. So, examples here, interrupted cutting and also machine motions. So you're doing a rapid, for instance, in your machining center or your turning center. It's very, very common. Most of us have heard parts of the machine, for instance, way covers, oftentimes, because they're thin, they're light, they're not very stiff. It's very easy to excite them. We hear it, okay, and then it damps out. However, the whole machine itself, okay, and individual parts, so spindles, boring bars that we'll talk about later, all those type of things can also, from a rapid motion, end up with free vibration. So forced vibration. So again, we'll get into that a little bit. So that is where we're driving the system at the excitation frequency. And it will only decay when we remove those periodic forces. So unbalanced, for instance, here, if we have a rotating mass that's unbalanced, and it doesn't matter whether it's the workpiece in the chuck of a lathe, or whether it's an unbalanced milling cutter, or whether it's a spindle that's or tool holder that's unbalanced, that driving misalignment, unbalance is going to drive as a forced vibration. Tooth passing frequency, especially in terms of milling, is also going to play into that. And then again, so the self-excited chatter. So it's the periodic response of a system to a constant input. And that input can actually be rather low. So, one of my favorite ones here is to think about somebody whistling, all right? So, when we whistle, it's a, we're not creating a very large force, right? We're simply blowing air through our lips, blowing air through a whistle itself. All right, and we keep it at relatively constant input, but the whistle or our lips, okay, begin to vibrate, and quickly become self-excited and start to create these vibrations that then, in that case, create noise. If we want to damp that down, then we need some limiting restraints. Just some interesting terms here. We're going to try to cover a few key points of some vibration theory. We're not going to go too deep into it today just because of time, but we want to get some things out there that hopefully will help you. So some things that play into machining dynamics and say as vibration as a whole. So one of the first things is the static stiffness, okay? And we can think about that in terms of like a spring element. So that's how much force is required per unit of displacement. Damping ratio is the ability of the system to dissipate energy. So that's what's going to help reduce that oscillation down, okay, as the impulse is removed. And then dynamic stiffness is pretty interesting because it's now a combination of those two parameters together. And that's really what's going to help control the vibration amplitude at the resonance. All right. You know, again, so chatter theory and stability. Chatter, again, it's a self-excited kind of vibration, all right? And it's coming in from the cutting force variations caused by variations in chip thickness and depth of cut. And a lot of times it comes in with the tooth being out of phase of the previous pass. Regenerative chatter, you know, in the end is when the dynamic forces and the displacement become out of phase. And we're going to talk a little bit about what that means. And hopefully this slide will help to make that clear. So this is a really good breakdown of looking at the tooth of a tool coming through and changing with chip thickness based on being either in phase or out of phase. So what do we mean by in phase and out of phase? I think that's really important for us to talk about here. You know, we're thinking about things as a waveform. So what I want to start with to kind of explain in phase and out of phase is, let's think about a child on a swing. If we have somebody on a swing, okay, so, and we're pushing them, right? So they're on the swing, happily going back and forth, right? So in phase would be, in terms of forces or an input, in phase is I'm pushing with them. They come back, I push them forward, they go away, they come back. We are working together to go higher, 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 higher with that swing, right? Out of phase means that we're not working together, okay? If I was 180 degrees out of phase, then I've got a situation where, okay, child's coming back at me on the swing, okay? I've been pushing while they're already gone, and I'm backing up as they're coming toward me. Okay, I'm not doing anything to slow them down, or I'm doing more to slow them down than I am to speed them back up, if that makes sense. One of the interesting things in terms of thinking about vibration and oscillation, you know, so often we think about it as a wave pattern, like I showed in the slides earlier. In terms of mathematics, how we approach this, that's definitely true, but you can also think about it in terms of the wave being around a circle, okay? So as we're moving with that sort of sinusoidal waveform there, you can also think about that as, in a sense, as rotary motion. And that kind of helps with explaining, thinking about that with the idea of the swing. So what happens when we're in phase or out of phase? So I'm going to go back to that slide so we can talk about this a little bit more. Let me share my screen again. Okay. All right, so let's go back to this to talk about being in phase and out of phase. So the first here over at the left, where I've got 0 degrees here, that is an example of a chip and an insert that are completely in phase. Because they're in phase, we have constant chip thickness. As I move to the right and I go 90 degrees out of phase, I'm starting to go thinner. I'm starting to go thinner. It's maybe not so bad, but it's starting to become a problem. When I get to 180 degrees, you see, that it's quickly becoming much more of a problem. If I go actually past that to 270, then things can start to become even worse, believe it or not, because of how I start to shift those two paths together. Basically, when I get to the point that I'm really thin and really thick, depending on that phase relationship, that is really what's going to cause chatter, okay? Because I cannot control my chip thickness anymore. My chip thickness is now a function of both my input in terms of my machining parameters and what the system is doing, and usually the system being the tool and the tool tip. There's some different ways that we can predict this, okay, using things like understanding of the system in terms of springs and dampers. And I'm going to move forward a little bit here. I want to talk a little bit about this in a little bit more detail. I'm going to come back to this slide. So I'm going to use this picture here for a second, and then we'll step away and come back to that. So how can I start to think about predicting what my vibration is going to be, and how can I control it? So in any system, we're looking at three components. So we're looking at the mass of the system, and possibly different masses that we'll get into. So if we have different masses and those masses can move relative to each other, then we have to start to treat them differently. And that's what we see a little bit here in this picture, where we have two masses. We also have the static stiffness, so essentially the system of springs or elastic elements. And then we have damping and damping elements. So I want to explain about stiffness and damping in a little bit more detail, and then we'll get back into this. So what is the difference? I think stiffness is fundamentally very easy for people to understand, right? Because it's, how much force do we need for a given displacement, as we defined earlier. And it's really easy to think about that like thinking about a spring. So we use that analogy all the time, and it's very, very valid. Damping sometimes is a little bit harder to understand. So in terms of, if we started to break this down into some basic equations of motion, we would be looking at the spring element going with displacement. Okay, we'd be going with the damping element against the velocity, so multiplied with the velocity of the system, basically, that the mass is moving at. So what's that really mean? The easiest way that I can kind of explain it is if we think about a shock absorber in a car, okay? Shock absorber is usually gas-filled or liquid-filled, right? And what you're doing is you're really relying on friction, usually Coulomb friction, to help offset, if we think about it, with increased velocity, we'll have increased friction, increased drag. What that will do is that will give us a stronger response against the motion as the velocity increases. Okay, so we basically start to come down to three parts of this balanced equation. So one is the spring element, okay, against displacement. One is the damping element, which is against the velocity that's moving at, and then the mass itself that we're dealing with along with acceleration. So those three elements will help counteract the forces that we apply and help us be able to calculate this. This is going to be really key to our topic today as we break down how the vibration-free boring bars work, and some ideas of how to use them and how to troubleshoot them. So we'll come back to this. Let me just back up here and talk a little bit about, I'm just going to introduce part of this topic here. about damping and where it comes from in different places. One of the things that you might hear about is process damping, and I just want to step through this for a second. So process damping occurs at lower speeds, so lower feed rates, lower cutting speeds. What's basically happening here is that's where we start to, as the speed increases here, okay, our waves get longer, get wider. All right, as that happens, we have more chance that as the tool tip is moving up and down, that it either stays in phase or comes out of phase. But as we start to stack those waves together, which is not necessarily our ability to stack the waves together, but the velocity that the tool's moving at, that's where we start to get some process damping based on rubbing, essentially, okay? And that will start to come into play as we talk later about things like stability diagrams. I'm just going to mention what a stability diagram looks like. Won't be able to go in as much detail as we'd like to today, but I'm going to talk about it a little bit. So what this is a prediction that can come about by several ways. So it can come about by calculations and by FEA. Often it comes about with a tap test. So for those of you that are familiar with performing a tap test with an impulse hammer and an accelerometer, we do that test or we make the calculation in order to find out what the fundamental frequencies are, where the natural frequency of the system is. From that, we can start to calculate curves like this. The other parts of this curve, so let's say where the peaks occur, have to do with where so it would be a combination of where the natural frequency is. It also then is a combination of the tool geometry. So how many teeth it has, for instance, so what's the tooth pass frequency. The other things that then come into play in order to turn this into a useful tool later is information about the material itself. And here we start to look at depth of cut. So, you know, if we think about it, if we go back here to this slide, ultimately, what are we trying to do? We're trying to keep that tool tip engaged with the workpiece material, and we're trying to keep a relatively constant chip thickness. If our relative vibration and oscillation is very low compared to our chip thickness, we don't have a problem, right? It's kind of where it's insignificant. That's more in the bottom part of this curve. If it's very high, for instance, we're really in trouble because it doesn't matter, you know, what we have. At some point, we're moving that tool more than we have programmed for a depth of cut, all right? And you can kind of think of those things. I'm speaking in relative terms here, so forgive me a little bit. But that's kind of where we start to see the bottom level where things are stable at a lot of RPMs versus the top level where we also then eventually top out even in one of the better and more stable parts of the curve. So let's jump back to this idea a little bit. Okay, so I see a question here. What do we mean by speed? So most of the time when we talk about speed, we mean RPM. There is a feed rate component in this as well, but for most of the stuff that we're going to talk about today, we're definitely talking about RPM or peripheral speed. So let's kind of go back to, you know, what our goal is in terms of trying to deal with chatter and vibration. It can be a little different, for instance, in terms of a milling tool versus what we're going to get into with a boring bar. So when we get into milling tools especially, so I think a lot more people are familiar with things like tap testing, trying to find the best speed that we're going to run at. And our goal there is when we use that type of analysis is that we're trying to calculate a speed to keep everything in sync, so that try to keep that chip thickness as constant as we can, so that we reduce those periodic forces. at the end of the day, that's the biggest thing that we're after. If those chip thicknesses are constantly changing up and down, we've created a periodic force coming in and out that's always given us issues, right? So we've got an impulse, then we've got, self-excited chatter after that. However, if we can keep that a little bit more constant, right, things start to get a lot better. So in milling, that's normally our approach, is to think about either conditions that will keep us out of the range of chatter, to think about tool geometries that make it easier by making a bigger sweet spot. All right, so when we get into unequal index tools, variable helix tools, some other things that we especially do with our end mills in terms of relief styles to add more process damping, all those things start to make that a broader range that you can work in, okay? But that's kind of the goal. The goal is to stay as matched up as you possibly can and then widen those sweet spots as much as you can as well. When we attack the boring bar problem, it's a little different situation. You could try to follow that same approach. You could find the natural frequency, first mode shape of the boring bar and choose to run there. However, in order to get the easiest plug and play solution that we can give to a customer, we're approaching it here a little bit differently. And so I want to go ahead. I've got some more stuff that we can get into with the vibration analysis, but I want to go ahead and start talking in more detail about the boring bars, how they work, and what you can do to use them. So give me a second here. So let's talk a little bit about what are we after here in terms of these boring bars. The first thing I just want to kind of talk about, because we talked about extended reaches, long overhangs, things like that. These ratios that you see here are very important. So the stiffness of the material. So we talked about stiffness, we talked about damping, we talked about the mass. The stiffness of the material is going to be extremely important, right? Because again, we need to, it's not just part of our vibration equation, but we're also thinking about that deflection in and out of the chip, right? So you can see that, if we go from steel to carbide, we can really increase the length to diameter ratio. However, even with carbide, we're going to reach a limit where it is very difficult to be able to work in a wide range of speeds and feeds without having some self-excited vibration. And that's where the vibration-free solution comes in. The other idea here is that, we want to make this as easy as possible for our customers. So, we have offered what we call tunable boring bars for many years. So typically the tunable boring bars did have a mass spring damper system that could be adjusted and tuned in order to help you run at the conditions that you would like. So we can shift that a little bit to tune it to that individual bar. The idea here with the bars that we're going to talk about today is to make these plug and play. So I'm going to kind of walk through a little bit of why, what the advantages are, and also a little bit about troubleshooting. So let's get into this a little bit. So what's a little bit different with the new solution that we're offering? So one of the first things is to think about these the different head design that's available and how this really changes. So one of the first things that I really want to emphasize is how short this head is, and then how strong the initial connection is there. So one of the things that we want to think about is, we talked about the different elements. We talked about the spring element. We talked about the damping element, but then also how important the mass itself is. By having this very short, lightweight head design, we're able to reduce the modal mass that's at the end of the boring bar. We're also able to bring the insert significantly closer to the section that we're going to use for the tuning, which is also very, very important. And we also create an extremely strong and repeatable connection here. So when we look at this serrated connection with the alignment pins, you know, that's really important. And then of course some very strong and secure bolts. So we're going to bolt that directly in, and we've got the coolant coming through the center. So one of the biggest things that I want to get across to people in terms of using any tool that you're doing vibration analysis on, or you're using a plug-and-play solution like this, one of the first things is you have to be repeatable. If you're going to do any type of tuning, for instance, you're going to use a tap test or any type of prediction ahead of time, you need to guarantee that you put the tool in the machine the same way every time, where it's going to have the same you know, stiffness, damping, and sprung mass, right? That modal mass has got to be repeatable. So things like length position, we're going to talk about that a little bit later, how important that is. But the length is very important, the mass is very important. And here, the stiffness is very important. And that's where this design will really help improve that. So we've got, you know, good coolant delivery. Also just point that out while we're here on the slide. So we've got chance for optimum life from that. Turn my pointer on here for a second. So we've got the coolant through, which is very nice. We've got several different styles of heads also that we'll talk about. So you've got different insert styles that you can choose based on how you would like to secure it. All right, so there's a special numbering system that's covered in the catalog that you can see. So let's get here. Let's talk about the bolt-on style head a little bit. So with this image here, you can kind of see overall how it's been reduced, how it's been lightened, how much closer the insert is now moved. So we've, again, reduced the modal mass, and we've moved the tip a lot closer in. This coolant pin, again, we talked about that, is in the coolant channel. You can see how much we reduced the weight compared to previous boring bars, and again, that we offer multiple solutions here. So some other things that we, you know, that I kind of want to point out is how overall we can put this thing together. So I want to go back and talk a little bit about how this works in a little bit more detail, and then we'll come back to best how to apply it. Okay. So I want to go back to this idea of what we have here in terms of a dynamic absorber. So we talked a little bit about what we wanted to do with a milling cutter, of kind of how we tune it, tune the speed to match the system's frequency. Not a completely different idea here with the boring bar, but the difference here is that the biggest change that we're going to make is we're going to add a dynamic absorber. And this is what's really critical to how the vibration-free boring bars work. So behind the head there, we have a section that does contain a dynamic absorber. So what that dynamic absorber is it's a mass, okay, that's basically a mass spring damper system. What's really interesting about that is that one of the things we want to think about is relative motion. So what do I mean by relative motion? So that second mass, okay, on its set of springs can move relative to the overall system. So what its purpose is, let's go back to the to the swing analogy here in terms of cancellation of motion. So we talked about in phase and out of phase. We talked about in phase as in the child's on the swing, we're pushing the child exactly when we need to increase that motion, okay? But if I was out of phase, okay, so I'm pushing at the wrong times, then I'm able to cancel out and stop the swing, right? And that's really what we're talking about here. We're talking about that we've created a mass spring damper system in there that's able to move inside the boring bar, okay, relative to the boring bar, and that will help to damp out the vibration. And that's really neat. So let's talk about what then makes it different from boring bars that we've offered before, because like I said, we've offered tuned boring bars for many years. The big difference here is that these bars are pre-tuned. That's probably the number one overall thing in terms of this product that we'd like to get across today, is that these vibration-free bars are pre-tuned at our factory. So that mass spring damper system has been tuned to match the first mode frequency of the boring bar. So what that means is that, you know, as a customer, you don't need to worry about doing the tap test. You don't need to install it, listen to it, try to hear chatter, try to make some adjustments to try to get it out if you don't have access to tap testing. We have tuned that bar for that first mode frequency, and all you need to do is apply it in a very simple way. When we look at the boring bar itself, so one of the things that we want to talk about here a little bit is how to install these. And what you'll find is you'll find on the boring bar that it is marked for the length of the shank. Okay, so you can repeat that. We talked about it earlier. You need to be able to repeat your installation every time with anything that's properly tuned. So we have tuned this at the factory. So in order to effectively use it, right? So you want to install it to the marked length on the bar. The other thing that I'd like to talk to everybody about today that really can help is how to make the overall system more repeatable. And that's where, in this slide here, we've got the split sleeve holders that are available for different machines. So where this comes into play is if we think about mounting of traditional boring bars. You know, so often boring bars are mounted maybe with a set screw style. So there's a set screw, hold it in place. Well, we've added a lot of elements that we might have to tune for in that case. It's not very rigid, so it's not fully encapsulated. We essentially have added a spring element with the screw and how tight that is that we might have to worry about. So really, really wonderful solution here from our engineering team is the idea of these split sleeves and the different split sleeve holders. So this can be installed on your turning center, and then the appropriate split sleeve used with what size boring bar you want. And what that's going to do is that's going to give you a very, very secure and repeatable solution to make sure that you're going to match how we've tuned that bar at the factory. So that's one of the things that's that's really, really, really interesting. So let's talk a little bit about some troubleshooting. So if you have problems with this, you know, what would you do? Again, you know, if you've bought one of these and you run into problems with chatter, the first thing is to make sure that everything is repeatable, everything is clamped properly. Is it extended to the right length? Is it clamped securely? Are you able to use one of the split sleeve holders? And look at that first. Another thing that you can look at is whether or not you can use a more positive insert. So if you've checked everything else and you still have trouble with chatter, that would be another thing to look at. So again, what would that do? Just kind of go back to our little short overview of vibration theory. You know, we've got, we need to worry about the force input, right? So if we're able to reduce the force with a more positive input, more positive cutting insert, then that will certainly help the situation. So those are a few things, you know, to think about. But, you know, again, just to reiterate, a tuned boring bar is only as good as your clamping. So if you're not able to clamp it repeatedly, you could have issues. But again, that's why this whole system is designed to make sure that you can install it properly and repeat that every time and have extremely good success with it. Yeah, so again, it's pretty straightforward in terms of catalog selection, in terms of length and diameter that you want. Again, you've got different heads that you can use based on the style of insert clamping that you'd like to use. And we really have seen many good successes with these boring bars, and look forward to those of you that haven't tried them yet to give them a shot. Somebody was asking here why carbide boring bars help against vibration problems. So that's a good question, and we talked about that a little bit in the beginning. With basically what the carbide boring bar does is it increases the stiffness. So we have essentially two ways that we can tackle this vibration problem, right? So, well, more than two, but fundamentally in terms of the bar design, we can make the bar stiffer and stiffer and stiffer. And that's essentially what the carbide is doing. But eventually, even with carbide, we're going to get to a length where it's still not going to be completely stable. So carbide is going to be better than steel. But then once we exceed what carbide can do, that's where the vibration-free bars come into play. So, you know, again, in that case, we're able to use a little bit of science and engineering to offset that vibration. Yeah, so I think, let me just check and see if we had any other questions come in. And I don't see any. So again, let's just kind of recap. So, you know, we talked a little bit about, you know, what vibration is, and we talked about it being oscillations. We talked about, you know, chatter coming from that, what makes it, obviously we know we don't want it, but why does it come into play? You know, probably just another thing to mention, we've talked in some of our other webinars about stiffness, you know, in terms of deflection. Again, this all comes into play because we're talking about essentially the spring element side of all of this, and how much deflection we have relative to force. So, you know, so keep that in mind in terms of your overhangs. Just in general, especially for newer machinists out there, you know, always check everything, right? So if you've got a setup that worked before, okay, and you're happy with it, keep in mind that everything has to repeat. Again, if we're talking about milling, for instance, stick out length has got to be the same every time. Tool holder itself needs to be the same. There's a lot of those things that come into play. Maybe we'll talk about it in later videos, but just keep that in mind that one of the reasons that we talked about some of that today is just to drive home the point that these vibration-free boring bars do have, let's say, an element of magic, okay, and that it's really neat that we're able to develop this system to pre-tune them and make them plug and play. However, to make them plug and play, again, that is where everything absolutely has to be consistent. So hopefully that helps you, gives you the confidence to apply them. And yeah, if you have more questions, please feel free to reach out to us either through Facebook. Later, when this is on YouTube, you can reach us there. Feel free to contact Kennametal support as well. So with that said, I'm going to go ahead and wrap the webinar up. I appreciate everybody that attended today, and I hope you all stay safe. If you like this video or have any comments for us, please feel free to leave us some comments, and yeah, like the video if you like it. And we again appreciate your time and look forward to seeing you on a future webinar. So thank you. Have a good day. Bye.